Hi everyone, my name is Ian. In this video, I would like to introduce Kaizen, a practical self-supervised continual learning method with continual fine-tuning. This work has been a collaboration with researchers from Nokia Bell Labs and the University of Cambridge. To begin, let's imagine the following scenario. You have bought a fitness tracker, and in the beginning, it might be able to recognize a few basic exercises like running and cycling. Over time, you might want the device to recognize a specific exercise that you do a lot, like rock climbing, for example. However, currently, if you want to do this, since these models are static, you will have to wait for months and months to hopefully receive a machine learning model update from the manufacturer, which might not even happen in some cases. So this is the problem that we're trying to target. How we can make models deployed on devices evolve over time. In particular, we want our machine learning models to learn brand new capabilities or the classes from a continuous stream of data with changing distributions. This is known as continual learning or lifelong learning. So, continual learning seems quite useful, but why don't we really see many applications of it? It's because there are a few unsolved research challenges that make it infeasible in practice. One of the biggest challenges in continual learning is catastrophic forgetting, in which a deep learning model forgets what it has learned when trained on new data. And this happens to almost every deep learning model naively applied in the context of continual learning. The plot on the right-hand side illustrates this. At the beginning, when a model is trained on an initial task, the accuracy slowly grows and reaches a satisfactory level of performance. However, once we have finished training on this task, when a new task arrives, the data distribution shifts. The model will very quickly forget what it has learned about the previous task when we train on the new data. With a dramatic drop in performance, it becomes specialized in the new task. The same happens when we switch again to another new data stream. If we do not care about the performance of previously trained tasks, this might be acceptable. But the goal of continual learning is to make model accumulate knowledge over time, rather than forgetting all the previous ones. So researchers have proposed different methods to mitigate catastrophic forgetting. Existing methods can be separated into two main categories, supervised and self-supervised. They all focus on how to retain the knowledge using techniques such as knowledge distillation. However, many of these methods make very unrealistic data assumptions. For supervised learning, they assume that we have many label samples per task to learn from each time. This is simply not practical because users will not sit there for hours and hours labeling data. Self-supervised methods try to mitigate this by training on unlabeled data with changing distributions. This solves the labeling problem but has a major flaw. Classifier is not trained at the same time because the method does not use any labels, so the model is not usable until this happens. This almost defeats the purpose of continual learning because the model is not usable until the final step. Therefore, we believe that continual learning needs to go semi-supervised while being robust to forgetting. In our work, we propose Kaizen, which aims to balance the two extremes, the supervised and self-supervised approaches with a much more realistic data assumption and usability over time. In particular, we focus on ensuring that the classifier is usable while learning new tasks. With continual learning, it is able to opportunistically learn from label data when it is available instead of waiting until the very last step like self-supervised learning methods. But it also leverages self-supervised learning to learn from unlabeled data for better generalization and representation, while reducing the dependence on labeled data. In this way, we can balance learning new tasks and knowledge retention. And in this section, I'm going to introduce the inner workings of Kaizen. To tackle the challenges that I've mentioned, we designed a unified continual learning scheme with 4 purpose-built components corresponding to 4 lost terms, and I will go through them one by one. First of all is the contrastive self-supervised learning module, which closely follows modern contrastive or Siamese learning methods. It trains the feature extractor to produce good feature representation by ensuring that the embeddings of 2 transformed views of the same input image to be similar. This allows us to make use of unlabeled data for training and reduces the need to rely on a large amount of labeled data. While the feature extractor is learning from the new task, the second components tackles catastrophic forgetting. This uses the feature extractor trained from the previous task to perform knowledge distillation, so that we can retain the knowledge from the old model. This is done by repurposing the same contrastive learning method in the first component, but this time the embeddings from the previous model and the current model are pushed to be close to each other instead. The third component focuses on label data training, where we opportunistically train the classifier if labels are available. This makes sure that we have a well-performing classifier during continual learning, rather than waiting until the very last step. Similar to the feature extractor, we also need to handle catastrophic forgetting for the classifier, so we perform knowledge distillation here as well, using the classifier and feature extractor from the previous task. Note that in this component, the classifier is trained even if the data is unlabeled, because we are performing knowledge distillation. This keeps the classifier in sync with the feature extractor, so that even if there are a lot of unlabeled data, the classifier can still perform well and stay in sync with upstream components. Combining these four components forms our proposed method, Kaizen. And now we will move on to evaluation, where we compare our proposed scheme to other existing methods. In terms of metrics, we selected 4 metrics that we believe can better reflect the performance of a continual learning model. First of all is continual accuracy, where instead of only looking at the accuracy at the final continual step, we take the average of the performance over time. This better reflects the performance in the entire life cycle of a deep learning model, where we want the model to perform well whenever we deploy it, and also in subsequent updates. Final accuracy, which is a standard metric, measures how well the model performs after the final training step. Forgetting, which is calculated by comparing the performance on particular task between the final model and the best intermediate model, measures how much performance is lost over time. Forward transfer compares the performance of a specialized model, which is only trained on a particular task, and that of the continually trained model. This is to measure whether previous knowledge helps in learning a new task. Although this is a desirable property, it is very hard to achieve. So now we have seen the evaluation metrics. First of all, we can take a look at the overall performance of the models on CIFAR 100. Here we have demonstrated that our method is compatible with different self-supervised learning methods, such as BYOL, SimClear, Mogo V2+, and VigRec. In the plots, the blue bars represent the performance of our models. We can see that it outperforms the previous state-of-the-art method, Castle, by up to 13.8% in continual accuracy. To better demonstrate how the models perform over time, we break down the overall performance into individual learning steps, where here in each plot, each group of bars represent the performance of different models at each continual learning step. We can see that the performance naturally decreases because the task becomes more and more difficult over time with more classes, as well as catastrophic forgetting. All models achieve similar performance after training for the first task, but our method enables more gradual forgetting over time, which results in higher performance at the final step as well as across time. Next, we performed an ablation study on the amount of data we played to the model from previous tasks. We can see that generally the performance and forgetting improves as we replay more data. However, at the same time, the forward transfer degrades because there is a trade-off between knowledge retention and learning from new data. It is also important to note that the model performs reasonably well when none of the samples are replayed. This can be useful in settings with stricter data assumptions, where we cannot store any label data for replay. So to conclude, in our work, we proposed Kaizen, a unified training scheme for self-supervised continual learning. Our method assumes a more realistic data availability compared to existing supervised or self-supervised continual learning methods, and it outperforms existing methods with a balanced objective in both knowledge retention and continual learning. Thank you very much for your interest in our work, and please feel free to get in touch if you have any questions, and check out our full paper and GitHub repo with links here. Thank you very much.